Good day, everyone. I am Graceful Jan Camanse, and I'm your reporter for this day. Elevation of crest and sag vertical curves. What is vertical curves? So vertical curves are the second of the two important transition elements in geometric design for highways. A vertical curve provides a transition between two slope roadways, allowing a vehicle to negotiate the elevation rate change at a gradual rate rather than a sharp cut. The design of the curve is dependent on the intended design speed for roadway, as well as other factors including drainage, slope, acceptable rate of change, and friction. These curves are parabolic and are designed stationing based on horizontal axis. There are two types of vertical curves. First is the sag curves and the second is the crest curve. So sag curves are used where the change in grade is positive such as valleys, while crest curves are used when the change in grade is negative such as hills. Both types of curves have three defined points: the PVC or the point of vertical curve, PVI or the point of vertical intersection, and the PVT or the point of vertical tangency. So as you can see in the picture in the upper part, that is the example of the crest curve where the first grade is positive and the second grade is negative. So in the downward, that is the example of the sag vertical curve where the first grade is in negative and the second grade is in positive. When are vertical curves applied? So first, at an intersection of two slopes on a highway or roadway. Second is to provide a safe and comfort ride for vehicles on a roadway. Table 15.16 is the values of key for sag vertical curves based on stopping sight distance. So in this table, it shows the design speed in miles per hour, the stopping sight distance in feet, and the rate of vertical curve k. So this table is very important for us to know the exact distance of the stopping sight in a designated speed of a vehicle. So the minimum length of a crest and sag vertical curves must be known if the elevation are to be determined, as was a case for formulas to compute length. The method for computing elevation relies on the properties of the parabola. So using the properties of the parabola, y is equal to ax squared plus bx plus c, where a is constant and b and c are 0. The location for the minimum and maximum points and the rate of change of the slope are determined from the first and second derivative. So where y, max or mean, is equal to 2ax, so that is the first derivative, and the second derivative of the function, which is equal to 2a. The horizontal distance between the beginning of the vertical curve and or the end of the vertical curve and the point of vertical intersection is equal to t1 equals to t2 and equals to t2, and the length of the curve L is equal to 2t, where L is in feet. So if the total change in slope is equal to a, then we can conclude that a is equal to a over 200L, or 2a is equal to a over 100L. Some additional properties of vertical curves exist. Offsets, which are vertical distance from the initial tangent to the curves, play a significant role in vertical curve design. The formula for determining the offset is listed below. So whereas y is equal to the offset is equal to the a times x squared all over 200L, where a is the absolute distance between the grade 2 and grade 1 multiplied by 100 to translate to a percentage, where L is the curve length and x is the horizontal distance from PVC along curve. The location of the high or low points of a vertical curve is used by the engineer to check constraints. As shown in the figure, the distance between the elevation at the beginning of the vertical curves or the PVC and the highest point on the curves can be determined by considering the expression. So whereas y1 is equal to the grade times x all over 100 minus the offset. So simplifying the equation, we can concluded that the value or the formula for the highest point of the vertical curve is equal to the L times grade 1 all over the grade 1 minus grade 2. So x high is the distance in feet from PVC to the turning point, which is the point with the highest elevation on the curve. So in equation 15.18 is also valid for sag curves. So similarity, it can be shown that the difference in elevation between the PVC and the turning point y high can be obtained by substituting the expression x high for x in the equation 15.16. So let's recall that the equation in 15.16 is equal to the grade 1 times x all over 100 minus the offset. So simplifying the equation, we can get the y high is equal to the length times the grade 1 raised to 2 all over 200 quantity grade 1 minus grade 2. Design procedure for crest and sag vertical curves. The design of a crest or sag vertical curves will generally proceed in the following manner. First, determine the minimum length of curve to satisfy sight distance requirements and other criteria for sag curves. Second, determine from the layout plans the station and elevation of the point where the grades intersect. Third, compute the elevation of the beginning of vertical curves PVC and the end of the vertical curves EVC. Fourth, compute the offset y as the distance between the tangent and the curve. Usually, equal distance of 100 feet or equal to one station are used, beginning with the first whole station after the BVC. Fifth is to compute the elevation on the curve for each station as elevation of the tangent, positive negative offset from the tangent y. For crest sag, the offset is negative and for sag, the offset is positive. So compute the location and elevation of the highest crest or lowest sag point on the curve using the following equation 15.18 and 15.19, where the x high is equal to the length times the grade 1 all over grade 1 minus grade 2, and the y high is equal to length times the grade 1 squared all over 200 quantity grade 1 minus grade 2. To appreciate the given formulas for the crest and sag vertical curves, we will use it to some examples. So example 15.4. So of crest vertical curves adjoining a 3% and a negative 4% grade is to be designed for a 75 miles per hour. If a tangent intersects at station 345 plus 60 at an elevation of 250 feet, determine the station and elevation of the BVC and EVC. Also, calculate the elevation of intermediate points of the curve at the whole station. A sketch of a curve is shown in the figure 15.16. So in this problem, as you observe, the first grade is positive and the second grade is negative. So it means that the vertical curve is sketched as crest, as shown in the figure. So first, to solve this problem, we need to find the value of k in the design speed of the 75 miles per hour. So in the table, the value of k for the 75 miles per hour is equal to the 312 feet. So we can calculate the minimum length by multiplying the value of k to the grade 1 minus grade 2. So the minimum length is equal to 312 times 3 minus the negative 4 grade 2 is equal to 2,184 feet. So we can calculate the stationing of the PVC and EVC, where the station of PVC is equal to the 345 plus 60 minus the minimum length over 2 is equal to 334 plus 68. So the station of the EVC is equal to the 334 plus 68 plus the minimum length 2184 is equal to 356 plus 52. So calculating the elevation of BVC, so it equal to 250 minus the grade 0.3 of the grade 1 times that the minimum length over 2. So the elevation of PVC is equal to 207.24. So kung matingala ka nga nung gigamit kay 0.03, it is because PVC is in the slope of 3%. So kung ang pangitaon kay ang elevation sa EVC, so imo ra nang alis dandra og 0.04. So for the last problem, a current railroad is climbing a hill at an angle of 3%. The road starts at the station 100 and elevation of 1000 meter. At station 110, there is an at-grade railroad crossing that goes over the slope road. Since designers are concerned for the safety of the drivers crossing the tracks, it has been proposed to cut a level tunnel through the hill to pass beneath the railroad tracks and come out to the opposite side. A vertical crest curve will connect the existing roadway to the proposed tunnel with a grade of negative 5%. The prospective curve will start at the station 100 and have a length of 2000 meters. Engineers have stated that there must be at least 10 meters of separation between the railroad tracks and the road to build a safe tunnel. Assume an equal tangent curve with the current design in this criteria meet. So as you can see, or as you can observe, the first grade of the problem is positive and the second grade of the problem is negative. So therefore, we can conclude that it is a crest vertical curve. So there's are many ways to solve this problem, but we will using the offset formula, where y is equal to the a x squared or over 200L, where a is the difference between the two grade. So plug in the given formula. So 3.5 times 1000 squared is equal to 200 times 2000. So it equal to 8.75 meter. The design does not meet the criteria since the engineers stated that there must be at least 10 meters of separation between the railroad tracks and the road to build a safe tunnel. So that's end to my report. Thank you.